All right, so in today's example, it's very similar to yesterday. So there are three restaurants, and the way that we're setting up this up is I've told you how many people are at the restaurant each week. So 200 at A, 400 at B, 800 at C. And I've told you the probabilities of movement between the different restaurants. And I've summarized that information in the transition matrix. I haven't given you the diagram today. And that's because we're going to use the matrix to do the calculations for us. And for the next couple of weeks, it'll be just matrices from this point on for transitions. Okay? So make sure you've got a copy of this matrix down. And the question that we are asking today is, what's going to happen next week? After 2 weeks, after 3 weeks, after a few more, and this long-term thing is called the steady state, which I'll talk more about towards the end. So you're going to need to get your CAS calculators out now. So grab them out. So look at this. It took 1.5 years, but I can finally project a CAS calculator to the screen in real time. Yeah. Okay, so it's exactly what you're saying. So start off by storing a matrix in a variable t. So what I'm going to do is I'm going to press Control and this variable button. So Control, and it's going to give me an arrow. I'm going to call that t. Okay? Once I do that, I'll have it stored and I can reuse that for other calculations. So I'll go ahead and type in the numbers for the transition matrix now. All right, so do that. It'll be longer for you because I've got a keyboard. You've got the tiny buttons on the CAS calculator. Check that T has actually been stored by just typing in T and pressing enter, and you should get the matrix back.
You only use, I guess, this function if your other question has multiple parts.
I would leave it to your judgment. So if you think the CAS calculator is going to help you, then use it. It's just a tool. So if you don't need the CAS calculator, then you don't need to go to the trouble of storing it in a variable like this. So do the work only if you need it. It's going to help you. Okay? All right. So that was our first step, to store t, because we're going to use it for some calculations. All right, let's go back to the question. We're going to need to set up another matrix as well. So if you were here in yesterday's class, we called this the initial state matrix S0. So please write this down. Yes, recursion is making a comeback from this point onwards. Grab whatever you need. So let's remind ourselves how many people were in each restaurant at the start.
200, 400, 800, 80.
Okay, great. So those are the numbers that are going to go into this matrix, S0. You can't do this question easily without this second matrix. So if you read a book, they'll call this the initial state, initial meaning the start or the beginning. So I think we should store this matrix in our CAS calculator as well. So go ahead and do that. Let's go back to the CAS calculator. And this time, we'll just call it S, okay? So create a new matrix. This time it's a 3x1 matrix. Control there to store, and we'll just call it S.
You could, like, can you, yeah.
What you can, but I would advise you not to, because you may confuse yourself. All right. Have you got the two matrices stored?
Yes.
Okay. Okay, so we've got two matrices, S0 and T. And I'm just going to write down some formulas now. The first formula is the recursion formula. So if I have some state Sn, this could be any week, so week 0, week 1, week 2. The way to get the next week, Sn plus 1, is to multiply the previous state by the transition matrix. Okay, so if I want S1, what I will do is I will do T times S. And I'll create another vector, sorry, not a vector, a matrix, with some different numbers. And that will tell me how many people are at each restaurant after 1 week. The other formula you need is a shortcut. So this is called a rule. Maybe I don't want to press enter 20 times, so you can just use this formula instead. T to the power of n times S naught. Okay, so I would suggest using this formula, because without this, you're going to have to start at S naught and do something like this each time. All right, it's going to get a bit messy. All right, so Sn equals Tn times S naught. That's our go-to. So let's go back to the CAS calculator now. Let's start by finding the number after 1 week. So am I going to do S times T, T times S, or does it not matter? Why does it matter, Jason?
Because the matrices growth
So remember, when you're multiplying two matrices, the orders have to match. Specifically, the number of columns in the first matrix and the number of rows in the second matrix. So if I try S times T, I'm expecting to get an error. Okay, if you ever get this message, this is good. It's good because you know you've definitely made a mistake somewhere and you can fix it. So let's do T times S. And you'll see the numbers have changed. It's now 400, 460, 540. And I believe this has a copy function. Screen capture. Let's see if this is quicker than writing it. Copy. Let's see. Drum roll. I mean, it's all right. I think I'll write something underneath as well. So Tn times S naught equals Sn. So here we found that S1 equals 400, 460, and 540. What does the first row tell me?
400 people will be at Cafe A.
Right, so because I set up my matrix like this in the order A, B, C, I have to remember that order when I calculate a new matrix. Okay, so the transition matrix and the state matrix need to have matching rows and columns, and remember the order. So I've done A, B, C. So after 1 week, we'll have 400 at A, 460 at B, 540 at C. Up until this point, I haven't said anything new that we haven't.
I feel violent. And slightly.
Can I continue? Okay. So we did most of this yesterday. The only thing that's new is this formula. Now, I don't want to do. I'm just thinking maybe it's not such a good idea to do all four. I think we'll be here for a while. So why don't we just do 7 weeks and the long term. So yeah, so I need to explain the long term to you because that's new. So right now we found the number of people in each restaurant after 1 week. And now I'm asking for after 7 weeks. So if you've been paying attention, you should know what to do at this point.
7 weeks.
Yep.
S7 is equal to T to the power of 7 times itself. 686.
Wait, oh. T to the power of 7 times S naught.
Great. So t to the 7 times s naught, because you've used the formula Sn equals Tn s naught.
It's 686.
In terms of the sack, will this be like more on the sack like this, or be like more like what we've already done?
So I am writing the stack at the moment. It'll mostly be applications. So applications means communication and dominance and transition matrices. So given that transition matrices is the whole chapter, you can expect most of the stack to be on transition matrices. All the algebra stuff will be assumed knowledge. And I'll show you how that comes into play in a transition matrix question. So going back to where we were before, t to the 7 times s. You got this?
Yep.
Okay, so my question originally was, how many people would you expect to be at each restaurant? I can't really have 0.003 of a person at a restaurant. Okay, so
missing a lot there?
not this discussion again. I had this in my year 8 class. They're missing an arm. Is it less of a person? Let's go with no. Okay. So 686. 0.0, 429.9, 284.1. And what you want to do is round to the nearest whole number for practical purposes. Is this okay?
Yeah.
So all we're doing is we're combining geometric recursion with matrices now. Okay, instead of a common ratio R, it's a transition matrix T. Instead of an initial term V0, it's an initial matrix S0. Okay, so if you're comfortable with that part of recursion, this is fairly straightforward. All right, last part is the long term. So what I want to do is show you what happens with the calculator if we let it go on for a while. So one of the interesting things that happens with transition matrices is often things settle down to a long-term pattern and it doesn't change anymore. Doesn't always happen, but in most of the applications in this course, we see this happening. So I'm going to put in t to the 100 times s. 100 is a pretty large number. You might need to go larger, but 100 is a good place to start.
Is this just trial and error?
Not just trial and error. So you'll see that it's actually kind of It's actually not 700. It's probably 699 or 700 with a long list of decimals. So if I go to a smaller number like 20, oops, not that, times s, you'll see it's already pretty close to 700. And if I keep increasing t, sorry, I should say the power of t, you'll see that it's getting closer to 700, closer to 420, and here the rounding is already too small. So in this case, around 20 was enough to get you close to your steady state. Okay? The way you check if you've reached your steady state is you need to check a large number and then increase the large number by 1. If it doesn't change much, you're at your steady state already. Okay? So I remember when I did maths 10 years ago, 25 was not a bad place to start. We could try 100. It all depends on the matrix you have. Some matrices do not give you a steady state, though. You'll see that when you do some exam questions later in the year. All right, so why don't I write this down? So try t to the n times s naught for a large value of n. Check that t to the n plus 1 is similar. So in our case, t to the power of 20 and 21.
So there could be multiple answers for that.
No. So there's only two options. Option number 1 is that you have a steady state and you'll round it to the nearest.
Oh, so you don't have to say what number you can steady state. No. Just whether you have a steady state.
But you need to show me what numbers you've used. Okay? Because if you just put in a really large number, you haven't demonstrated that you've actually reached the steady state. You have to check that it doesn't change one evolution number. So having both numbers, 1 and the one after, is very important for this. Okay? Because if there's no steady state, it's constantly changing, a large number won't give you the steady state because there is none. So to answer your question, Tom, either you have a steady state and it's going to be the same after rounding, or there is none at all. Okay? And that's why you've got to check. So in this case, it was 700, 420, and 280. All right. You okay with this? Can you give me a nod if you're feeling comfortable with what the example we just did? All right, about half of you. We do need to keep moving. I think if we need to slow down by 1 class, we can do that. But probably not much more than that. So maybe I can delay this like by 1 day or something. Okay. I'm now going to do an algebra question with you. But the good news is, because I've done it, you won't have to do it.
Yeah.
Okay, so this is actually quite a difficult question, and I wouldn't expect you to come up with the answer yourself if you hadn't seen it before. So this is 11C, question 3. And this is our last example. So in this question, we are told we have a transition matrix, T equals 0.65, 0.35, 0.4, 0.6. And we are told that S5 equals some numbers, 5461, 4779, and your task is to find S4 and S3. Can anyone tell me how this question is different from the one that we just did previously? What was that, Tom? Going backwards. Well observed. So this equation in purple is what you already know based on your recurrence knowledge. So I'm going to help you out. S5 equals T times S4. I've set n equals 4. So if I were going forward in time, I would multiply by T to go from time 4 to time 5. The trouble is, I know S5, I know T, but S4 is unknown. I want to solve, hint hint, a matrix equation for S4. No? What was that, Jazz? Power of negative 1. You're on the right track. Which matrix will get the power of negative 1?
T.
One of those ones will give you the power.
That's wrong.
Okay. It is T.
Yeah.
It can't be this matrix because you can only take the inverse of a square matrix. This is not a square matrix. Okay? This one is a square matrix.
So what if you don't have a square matrix? For T.
You won't have a transition matrix. Okay? So, we're going to multiply both sides by T inverse. So you don't have to write this. T inverse times S5 equals T inverse times T times S4. What happens when I multiply a matrix by its inverse? That's right. It's the identity matrix, which does nothing when you multiply by it. Okay, so what we've shown is to go backwards in time. Instead of multiplying by T, we will multiply by T inverse. Similarly, once we've got S4, we can multiply by T inverse again to get S3. So grab that down, and then in a second, we will do this on the CAS calculator.
Wait, if you already have one stored as T, and you just press, then you want to store a new one. That do.
You can put it into T. Yeah. So the danger with storing variables is you can forget that you've stored them and it can stuff up all your calculations. The way that I get around that is to clear everything before the start of every session. So I'll show you this on the CAS now. If I've decided that I don't want to use T anymore and go back to a fresh slate, go to Menu, option number 1, Actions, and option number 4, Clear A to Z. This is going to clear all your variables. And you'll see Clear A, Z comes out. And now if I type in T, I just get T. Okay, so you don't, in general, we don't have to do much of this, but in the other maths classes, they have to worry about this a lot more. So, maybe not foundation, because they don't have a CAS calculator, I think. Yeah. So just the methods, kids. All right, so go ahead and store the matrices. So we'll type in a 2 by 2 matrix. 0.65, 0.4, 0.35, 0.6. And this is going to go in T. Sorry?
You save a variable as grade, and then A to Z doesn't clear when there's multiple letters. So now he just has Greg on his
Oh, okay. We can sort that out. That's all right. Maybe not right now.
Right, Greg. And it's fine. Greg is a
You shouldn't have to clear history.
Okay. So, by storing the variables, this is going to make our life easier. Now, S in this context actually means S5. Oh, that's a word, isn't it? Never mind. Sorry. So, what you want to do is multiply S by T inverse. That'll give you S4. And you can do it again. You can actually do -2. The calculator will recognize that.
And that will give you -1, 2.
Sorry, what was that?
No, but because he's done, if he did the last one by, I know, wait, no, yeah, because he did S, you can do the answer. I see where I went.
Sorry, 1 second.
I've lost orientation.
Okay, so year 12. If I can have you listening. I appreciate your patience during a time when the topic is getting quite heavy. The next lesson is probably the heaviest one. So I'll just show you what's happening. Next lesson,
Tom's really strong.
we're going to add on another matrix at the end of our recurrence relation. Yeah, so this is called culling and restocking. Well, exactly, that's the point. So if this is modeling, like, say, a feral pest,
I mean, the human population, so.
maybe the ethics are a bit questionable there.
I mean,
I reckon arguing the Holocaust.
Your talks, listening? So I'm not going to cover this today, but be on the lookout for this on Friday.
Well, that looks disgusting.
Well,
That looks easy.
we'll get through it.
You're just adding another letter.
You are.
You're just adding to the.
You're adding
just
lines.
You're just a letter for another. Yeah, so is it just, would it just be.
You can do it all in chat.
That's right.
That's not bad.
Regular's fun. Do check and back.
Did Thanos also kill half of all species?
Did he kill all the half?
So if we could just pause this conversation for a second. Jason, you had a question?
Yeah, can come here, so
Sure. Okay. Are there any burning questions that you'd like me to answer now that are relevant to the matrices? That's what I thought. Okay, you can now start exercise 11C or get up to date if you're not up to date yet. Thank you.
Well, what if
So what about irrelevant?